So, Sumit, are you okay with recording
Yeah, that's
the
fine.
presentation? Okay, all right. Okay, so I think we are at 11 o'clock. Let's see. I think we can start. So, um, let me introduce our speaker today. Thank you everyone for joining. We have today Dr. Sumit Paudyal. Dr. Sumit Paudyal is eminent scholar, chaired associate professor in the Department of Electrical and Computer Engineering at Florida International University. Dr. Paudyal received MS in Electrical Engineering from the University of Saskatchewan, Canada in 2008 and PhD in Electrical Engineering from the University of Waterloo, Canada in 2012. He was a faculty member in the Department of Electrical and Computer Engineering at Michigan Technology University from 2012 to 2019. He is the recipient of National Science Foundation Faculty Early Career Award in 2018 and Eta Kappa Nu Best Professor Award for Teaching at Michigan Tech in 2018. He is currently serving as an associate editor for IEEE Transactions on Smart Grid and IEEE Transactions on Industry Applications. Dr. Paudyal's recent research activities include distribution grid modeling, optimization application in smart grids, and power systems control and protection. And he has been supported by NSF, ARPA-E, and DOE. So Dr. Paudyal is going to talk to us today on recent advances in mixed integer distribution grid, optimal power flow, modeling, and application. Thank you, Dr. Paudyal, for the talk today, and I'll hand it over to you.
Thanks, Anamika, and welcome everyone. So I'll be talking about what are the recent advances in mixed integer version of distribution grid optimal power flow. So I'll talk about mathematical models and some applications where we can apply the mixed integer type of control on the distribution feeder. So I work at FIU, so I can skip this slide since Dr. Dubey already introduced. And I would like to acknowledge the work supported by National Science Foundation and ARPA-E and DOE. So today I'll be talking about very high level background on distribution OPF, particularly focusing on what are the modeling challenges on the OPF at distribution level and why that is different than the transmission level OPF problems. Then I'll talk about the state-of-the-art DoPF methods, particularly focusing on the mixed integer version of the models. So we'll talk about mixed integer nonlinear programming models, mixed integer convex formulations, and so on. Then our group has developed different version of mixed integer DoPF models, particularly the mixed integer second order cone programming model and mixed integer linear programming model to dispatch the legacy grid control devices like load tap changer cap banks, which require the integer modeling. So I'll talk about some initial results that we have. Some of them are published in the paper. Some of them are, we're planning to submit soon. And then followed by the conclusion. So this is the very high level overview of what optimal power flow problem looks like and why we need that. And then this applies to the transmission level problem as well as to the distribution level problem. So we're basically aiming at obtaining some optimal decision for operational or planning of the power grid. Most commonly used objective functions are the cost optimization at the bulk transmission level. And then in distribution side, we see most of the work focused on the voltage deviation or the loss minimization type of objectives. So here we need to solve objective functions subject to a bunch of constraints, and those constraints relate to the physics of the grid. So you see here equality constraints, which are the power balance equations, voltage drop equations. So those are coming from the physics of the grid, and then we have a bunch of inequality conditions, which are basically related to the operational limit. For example, the voltage bounds or generation bounds on the power network. So this is the general structure of the OPF. So you can modify the set of constraints depending on the applications, and you can choose the required objective function of what you're aiming for. from these optimization problems. So where OPF is used on the bulk transmission level, so this has been used quite extensively for system operation, like scheduling the generators in day-ahead or real-time market. You can also use that optimal power flow. So this is the co-product of the OPF models that is called the locational marginal price, which basically gives you the energy price of the on the grid at different nodes, which could be different because of the congestion and losses on the network. So those are the some applications where OPF has been extensively used in the transmission level problem. So on the screen you can see that this locational marginal price and the MISO footprint was actually obtained by solving some version of the optimal power flow problem at the bulk transmission level. And we also need to understand the operational philosophy of the conventional power grid and how it changes with the in the distribution system. So if you recall your power system operation courses, then we basically need to track or work, schedule the generators to follow two type of signals. One is the slower changing dynamics, and other is the faster changing dynamics. So for the slower changing dynamics, we usually dispatch or schedule the generators that could be updated every 15 minutes or hourly or sub-hourly interval. And for faster control, typically the large generators are equipped with the automatic generation control, where the control center sends the signals every 1 to 4 seconds to update the dispatch of these generators to maintain power balance on the network. So here you can see that this slow changing dynamics or the scheduling of the generators could be done based on some optimal power flow type of models. So and then that's what is being used in the industry, either to dispatch those regulatory generators or do the market clearance based on some optimal power flow type of models. Now, the philosophy in the distribution side, so that was on the bulk transmission level. Now, on the distribution side, and the medium voltage and low voltage side of the circuit, now we're seeing level asset, for example, the DERs and flexible loads. So the question is, can we achieve the same type of grid functionalities that we usually achieve from the large generator and the bulk transmission level? And can we scale up the models and methods so that we can aggregate these resources, small but distributed resources, in real time, and then provide some support not only to the distribution level but to the transmission system operation as well. So since the control points are evolving on the distribution side, so we could use the same philosophy of optimally scheduling those grid edge devices and then provide some sort of support to the grid services. So that could be like the whole bar support on the distribution side, or you could aggregate them optimally and provide some sort of frequency support on the bulk power grid. So and then some motivational statistics why we can do that, or we want to achieve that, is we are seeing large penetration of these small but distributed resources in the medium voltage and low voltage side of the feeder. So we have seen very increasing penetration of the small photovoltaic panels with smart inverters on the residential customer level. And then we have a lot of EVs and flexible building loads, dispatchable building loads, without making any compromise on the quality of the service or discomfort to the end users. So all these are very motivating statistics that it provides flexibility on the grid edge, which could be tapped to provide the services on the grid. So now, to achieve that, so we envision that we need to solve some sort of the optimization problem similar to the optimal power flow that has been solved on the transmission, or the bulk power grid quite extensively. And there we see the value of the, developing and solving the efficient distribution optimal power flow models. So on the DoPF side, or the distribution side, so we have in the literature we have seen this type of models is quite extensively used for various applications. So I have just listed a few of them, but once the framework is ready and once you have the controllable devices, so you can tailor your DoPF model the way you want to achieve any of the operational objective or planning objective. So it's the list is not comprehensive here, but you can generalize your the applications and the value of the DoPF model. Now, one thing we need to understand is so why distribution grid optimal power flow model is challenging with respect to the compared to the transmission system optimal power flow problems. So in transmission level, we usually assume that the loads are balanced, which is not the case in the distribution. So we have to deal with the unbalanced circuit. In transmission system, we typically have the sequence networks decoupled. So you can most of the OPF problems are solved in the positive sequence framework. That since the circuit is balanced, negative sequence can be conveniently ignored without losing the accuracy of the solution. But in the distribution side, since they're highly unbalanced, even if you try to solve the sequence network, they are still coupled. The sequence network is still coupled, though the coupling could be weak depending on the feeder configuration and unbalancing of the unbalance of the loads, but they're still coupled. So this does not give much benefit for changing the domain of solving DoPF from the phase frame to the sequence frame, because still solving the coupled sequence network and you have to deal with the large matrices where its phase sequence components are still coupled and are similar to the phase components of the distribution grid. And then we have more control nodes and the distribution feeders compared to the transmission network, because in the bulk power grid we are thinking of 100 to 1,000 generators control. Here we could have tens of thousands to million devices on the grid edge, and so more decision variables, more controllable nodes, that will also make the DoPF challenging to scale. And one important thing to look at is also the integer control, which typically does not exist on the transmission network unless you are doing the transmission line switching problem. But the integer control variables are very common in the distribution OPF. For example, the load trap sensors, cap banks, and also the network switches. They only take the discrete or binary the variables. So we cannot find a solution that takes the continuous value for those equipment models. So we need to retain the integer model in the DoPF for the accuracy and also for the feasibility of dispatching those resources. And the last point is in the unbalanced system, we have all sort of transformer connection on the distribution side. While in the transmission network, we only focus on the a single phase transformer, equivalent single phase transformer, which is same as Y-Y connection. But in the distribution, you probably need to deal with the delta Y transformer as well. So these equipment details in a comprehensive model also makes the DoPF more challenging problem to solve compared to the conventional the OPF that has been extensively used in the transmission level problems. So how do we handle some of the computational complexity mentioned here? Typically it's done in the time scale separation. So the control is in the distribution system is decoupled into a slower and faster control approach. So you can see that for the slow time scale control, we can dispatch any of the resources, including the integer control or the legacy grid devices like the OLTC and cap banks, also the battery storage, and any flexible loads and DERs. So we could send the update signals of these controllable resources sub-hourly interval, and then they take the most of them take the binary or the integer values. For example, the load tap sensor takes the value from -16 to +16 at the interval of 1. The cap banks could be integer, and then number of integer point depends on the how many cap banks you have on the system. So all the integer and binary variables, I think we could dispatch that at the slow type scale given the computational complexity that will arise from the mixed integer type of problems. Then for the slow dynamics, the applications are like the voltage regulation, the control of these devices, and then you can think of the application as the whole bar control, network reconfiguration problems, or it could be continuously updating at the regular intervals the smart inverter mode settings. So all these are kind of a slow changing. The control, slow acting control on the distribution feeder. And on the other hand, you also need to deal with the faster dynamics, and then there you cannot really leverage the slow changing, the equipments that we have used in the slow changing dynamics, like the integer control of the OLTC and cap banks, because you need to solve this OPF model at the very fast time scale, maybe a couple of minutes or sub-minute interval. There we could leverage only the continuously controllable resources. For example, the flexible loads and DERs, active and reactive power, battery storage, electric vehicles, and so on. Their control charging. So and application-wise, it could be you could use that for the fast voltage control or frequency regulation kind of service that requires solving your OPF model at at finer resolution compared to the volt var regulation problem, which is kind of a slow time scale problem. So today we'll be talking about the mathematical models that pertains to the slow time scale problem. So the model that I'm going to talk next basically fits into this box here. So here we're gonna dispatch the OLTC cap banks, and also it could extend that for dispatching the network switches as well. So and that's where the application that we are aiming for is mainly the volt var regulation type of application. So to give you a high level summary on what exists in the literature for the mixed integer type of problems. So the nonlinear programming version with the integer, which makes the problem mixed integer nonlinear programming in nature. So that is also used in the literature. The benefit of using the MINLP is this is accurate model, because this is the exact way of writing the power flow and all the discrete control devices in the OPF framework. But you cannot scale this because of two issues: a nonlinear NLP model of the power grid, and then the integer problem, which is coupled with the nonlinear grid model. So this makes this MINLP problem extremely difficult to scale. Then you will also find a bunch of approaches in the literature where they relax the integer variable and convert the grid model into NLP, and then they solve the NLP. Again, it has computational challenges that you cannot really scale the NLP for large scale feeder, though we have recently done some work where we have seen that certain version of the NLP scales better than the others, but still this being the non-convex problem, so in general this is a hard problem to solve. And then once you have solved the NLP model, then you apply the rounding heuristic to convert that continuous the relaxed version of the integer variables to the integer variable. But then, in our one of our work, so we have shown that, this rounding heuristic is also combinatorial in nature. So if you have only few tab changers or OLTC cap banks, which takes the integer variable, you can come up with the efficient way of rounding it. But once that number of devices increase, then it becomes combinatorial to find out whether you should round up or round down, those variables to make the problem AC feasible, that is feasible to the original nonlinear model. So rounding heuristics may work for the small scale system, but it will not work for the larger network. Then recently we have seen, a lot of work in the continuous domain. People are using the second order cone programming and semi-definite programming. And we have also started seeing the papers coming out with mixed integers semi-definite programming, where the underlying grid model is the STP, and then they add this integer variable model for the cap banks and OLTC to make the problem MISTP in nature. So again, this has the scalability issue because the problem size grows for the semi-definite programming, has to deal with the large matrix size, and hence the STP in general does not scale for the large scale feeder. And then with inclusion of the mixed integer variables, the problem becomes even challenging to solve. Then you will see several works that uses the mixed integer linear programming model, where they rely mostly on the Lindis flow type of model for the modeling the distribution grid, which is a valid model for a single phase feeder or decoupled three-phase feeder. So the Lindis flow does not account for the mutual coupling of the phases, and hence it can introduce some error on the voltage. But you can find this type of models also in the literature, and this scales so well given mixed integer linear programming. Though it's non-convex, the solvers are really robust, and you can scale this problem to large feeder without any issue. I mean, this MILP nature of the problem. So then, just to go over some of these models in a little bit details, MINLP version is the most primitive one with nonlinear model of the grid and the integer control of the cap and tab operations. And then this is non-convex. It doesn't scale up. We have tried this in small scale feeder. We're not able to even solve 100+ node feeder with this type of approach. Then, I think in the MINLP version, so here's some details what you need to model. So, and this applies to all the models, all type of models. So you have to model the three-phase components, series sound, network equations, current balance equations, voltage drop equations, and operational limits. So this basically constitute your equality and inequality condition in the DoPF framework. So this one does not scale up. Then, like I mentioned earlier, then people have tried relaxing the integer and making it NLP. And then in our work, one of our work, so we have shown that relaxing the integer can make the AC infeasibility, can lead to AC infeasibility. For example, just take this 3-bus example, and then you relax this OLTC model by integer variable by continuous variable, and then you can see that the continuous solution lies on the feasible region. So this region represents the voltage within the bound of 0.95 to 1.05 per unit. And then once you have this continuous solution for the OLTC, when you round them up or round them down, right? So it could lead you outside this feasible region. So your voltage could go on this bus. For example, here's given in terms of the V3. It could lie outside the feasible region. So now this integer solution, so this continuous solution is feasible to the the original AC power flow equations, but this integer solution is not feasible because the voltage constraints are violated. So this is a very simple example to show that how the rounding heuristic may not work. So if you round down here, it may work because still within the feasible region. But when the solution is closer to the lower voltage bound, when you round them down, then you're still outside the feasible space. So you can come up with some sort of rounding heuristic, whether you want to round up or round down. Again, that heuristic will be combinatorial in nature as the number of integer devices increases on the network. So in general, we concluded that the rounding approach is not scalable to large scale feeder, or else sometimes it also does not give you any feasible solution at all. So then we started looking at the second order cone programming version of the OPF formulation, and then our objective here is to build the mixed integer second order cone programming, where we can include the OLTC and cap bank models using the mixed integer linear formulation, and then the conventional the grid model will be based on the seminal work by Stephen Lowe, that is the second order cone programming model. So the idea behind here is, this work does not include the integer control. So what this work basically does is it convexifies the branch flow nonlinear equation, which which makes the problem NP hard to solve. They convexified by using the second order cone, reformulation of that branch flow equation. So this scales well, and then it has been shown that the convexified model is generally tight. You have to be selective about the objective function choice, and it needs to hold certain condition on the grid. But in general, we can use this model to solve the continuous version of the DoPF problem. So what we did on this model was we added the integer formulation of the OLTC. So if you know how the OLTC should be modeled, so it's basically a voltage relation in terms of the tap operations. And since we write the voltages of the second order cone programming model in the square of the voltages, so this becomes square term, and then this is nonlinear model, so it adds computational and modeling challenges to fit within the scope of the MISOCP framework. So we introduced some auxiliary variables, and then we reformulated this problem by using the McCormick envelopes, and then we are able to obtain a MISOCP version of the DoPF, including the integer control of the load tap changes and cap banks. So on this flowchart, you can see that the work by Stephen Lowe is basically highlighted on this box, where they do this OPF angle relaxation and conic relaxation. Then on top of that, so we basically added the McCormick envelopes and then come up with this MISOCP model. Then when we solve this, so the McCormick relaxation is basically adds the convex envelope around the bilinear terms, and then it introduces some error, so in approximation error. So to overcome that approximation error, so we basically develop this sequential bound tightening algorithm, where in every iteration, so we shrink that the envelopes of the McCormick bounds until we get a tight enough solution to satisfy the constraints of the OLTC model. So so this requires iterative way of solving a series of MISOCP models. So you can see that in the first iteration, so we put this bound on the bilinear term, and then as we move along on the iteration, so we added additional convex envelopes around that to make that a feasible space more tight for that bilinear term, and then eventually we got the solution exactly lying on this bilinear curve. So here's the algorithm to tighten that the bound for the McCormick envelope every iteration. So it solves a series of these mathematical model, that is problem P, through this sequential bound tightening algorithm. And then so this is the observation in terms of the computational performance of the MISOCP for a small scale feeder. So we haven't really solved the large scale feeder yet for using this approach, but this one is published in this reference, and 125 100 plus buses with the 8 OLTC model on it. And then we basically solve multi-period DoPF, and to increase the problem size, we increase the number of the number of period in the multi-period setup. So as you can see on the screen, as on this figure, that as we increase the number of time step on the multi-period setup, the number of variables will be increased, and hence the problem becomes more challenging to solve. So, and you can see that we have tried a bunch of solvers, off-the-shelf solvers, that can solve the MINLP model, and we compared their performance, and you can see that I think the Nitro is the most robust solver that can solve the MINLP type of model. It also fails after the when we increase the problem size to 10 times step. The other solvers like Baron and I think we tried Baron only on this one. So it solved, even failed before around number of step equals to 6. But you can see this blue line, which is the MISOCP version that we developed, and we solve using Mosaic solver, and it basically linearly scales with the problem size. Still, the solve time is a couple of minutes, but which is acceptable, I believe, because given the nature of the slow control of the OLTC and CAP banks, we dispatch the OLTC and CAP banks maybe sub-hourly interval. So with thinking that as a time frame to obtain the solution, these solve times I think is acceptable. But again, this is not really a large-scale feeder, so we are working on to test the performance of this, and 2500 node feeder. So how does this model perform? Whether we can solve it within the 15-minute interval, or a 30-minute interval, depending on at what frequency you would like to dispatch the OLTC and CAP banks. So this is one version of the mixed integer formulation. Then we also so here we formulated the nonlinear OLTC model, mixed integer nonlinear OLTC model, using the McCormick envelopes, which requires iterative bound tightening algorithm. But here in the second approach, so we further modified that, and then we came up with the exact reformulation of the OLTC model using the mixed integer linear programming. So you can see the set of equations here that basically represents this nonlinear model by using some binary variable and auxiliary variable, and using some big M approach, we can convert the mixed integer nonlinear model of the OLTC to the exact mixed integer linear model. And here, this does not require the iterative bound tightening now, because this is the exact reformulation of the MINLP model. So then we plugged in this into the SOCP model. Then it worked. This is what we obtained the mathematical formulation. So and then we tried that for the different objective function, loss minimization and loss plus voltage deviation, loss plus voltage deviation, plus the tap operations. We need some additional constraints depending on the choice of the objective function, to reformulate that objective function as a linear model so that it fits within the scope of the MISOCP. So this is how we developed the mathematical formulation that could be used for the different objective function choice. Again, here you have to be mindful that the SOCP comes with the limitations. So we cannot really use the SOCP model for any arbitrary choice of the objective function. That's why you can see here, we have designed this objective function such that each of the objective function has the loss minimization component on it, because this will kind of ensure that your SOCP solution will be tight. If we ignore this loss term, then we have observed that only for the voltage deviation minimization or voltage deviation plus tap operation minimization, so this model does not give yield a tighter solution. So by adding some portion of the loss in the augmenting that in the objective function, we have seen that it helps to make your solution tighter or the MISOCP framework. So we use this on the 2500 node feeder, 2500 plus node feeder, obtained from the IEEE 8500 node feeder, where we added the 4 LTC control and 100 PV. And then we tried with the different choice of objective function. So you can see here the J1 represents the loss minimization. So you first can look at this figure here. This is with the loss as an objective, and then this is the voltage deviation plus loss as an objective. You can see that when you only consider the loss, the voltage profile on the feeder kind of spread, to a large reason. So it basically goes from 1 per unit all the way to 1.05, and it's spread in the based on the node. So it's basically the count of this shows the kind of histogram where you have bus voltage and how many times that bus voltage is close to this bar chart. So it shows how spread the voltage profile on the feeder with the loss as an objective function. And then when we added the voltage deviation as an objective function, then it kind of shrinks. So this basically shows that now the voltage profiles are pretty much smooth or kind of flattened because the frequency of occurrence is more around 1 per unit. But when you look at the number of tap operations in doing so, which is our intent because we're solving the mixed integer problems, with the loss minimization, the total operation of tap came out to be very large, 1068, which is not acceptable because that every mechanical devices like the tap operations comes with the life cycle that after a certain number of tap operation you need to do some maintenance or replace that tap setting mechanism. So to prevent that, I think this objective function J3, which has a component of limiting the number of tap operation as well, so it substantially reduced the tap operation to 10 per day. So this is really a good, in terms of reducing the tap operation and improving the life cycle of increasing the life cycle of the tap operations. Now, one thing to discuss here is the, so as I mentioned earlier, so the reformulation of this OLTC has some big M approach. So, and then we found that this is sensitive to the choice of M. So the big M is basically a very large positive number. And depending on that, the solution and the time are sensitive to that big M. And in some of the cases, we found that we were not able to solve within the given time limit. So you set a time limit of 30 minutes, and then with the objective function J2 and J3, I think in 2 instances we were not able to solve it. But in most of the cases, we were able to solve it with within the 900 second, which is 60, so like 10 minutes, 15 minutes time frame. Yeah, so that is the so that basically indicates we could get the solution within that sub-hourly interval of even for the large scale feeder. But again, given the modeling approach we have chosen with the big M approach, so you see some issues here that it was not able to solve, and then based on the choice of M, the solve time was also changing. So we have to be very selective on how we choose this big M. But then what we did next was, so we found another approach that we can exactly reformulate the MINLP to MILP even without using the big M, and that method was more robust than the MISOCP, which we have used in the next version of the model, that in the mixed integer linear programming model. So so far the SOCP based model, the MISOCP based model is is performance wise is okay, but you could still see some issue there for the choice of the the parameters and the OPF framework. So now another issue of the SOCP model is, like I explained earlier, the SOCP model ignores the mutual coupling, and then so does the Lindis flow based model. So then we have to basically come up with the models that can incorporate the mutual coupling as well. So Lindis flow-based model, it ignores the mutual coupling. In SOCP-based model, it ignores the mutual coupling, and it introduces large error on the voltage profile. We have done some preliminary work using the 123 node and 650 node feeder, and we have seen that SOCP and Lindis flow model, sorry, the Lindis flow model and SOCP model, they basically have large error with respect to the three-phase power flow solution. And then the closest one that we saw was the Lindis three-flow based approach. Even though the Lindis three-flow ignores the losses, their voltage profile was the closest to the nonlinear power flow with the mutual coupling. So then that basically motivated us to try the including the linear model, the integer control model to the linear model of the grid using the Lindis three flow based approach. And this is what we come up with. We have linear Lindis three flow based base OPF model, where you can see that this has the mutual coupling effect included. These are the modified admittance matrix, which includes the mutual coupling effect. And then we added the exact reformulation of the integer control variables, mixed integer nonlinear formulation of the OLTC was reformulated as the exact MILP formulation. And by combining these two models, so we get the MILP model that we can use to dispatch the OLTC in CAP banks. And then this is some of the case studies, preliminary results that we have. So we have not published this work yet, but we are in the process of submitting this to a transaction paper. But what you can see here is the on the 123 node feeder with the 4 OLTC control, the solution obtained from the Lindis 3 flow based OPF, and when we benchmark that with the OpenDSS models, there are some errors, but that error is less compared to the SOCP version. So we accepted this as the improvement over the SOCP, and then applied this to the 2522 node feeder with 5 OLTC, and then you can see we were able to solve this voltage deviation and tap operation minimization problem. And you can see how well this voltage is positioned around the 1 per unit on the entire feeder for each phase. And then this shows the number of tap operations throughout the day using this MILP based model. And then this is more accurate than the MILP version you can see in the literature, which only use the Lindis flow version that ignores the mutual coupling. So that's the the case studies. So on the conclusion, so we have seen that the DoPF are the use of DoPF are increasing in the distribution grid planning and operational problem. The one major issue that we have seen is the scalability of the model and the solution algorithm that we can apply for the practical size grid, and also it has to be accurate as well. The MISOCP outperforms MINLP, and then it linearly, the computational need of the MISOCP or computational speed of the MISOCP is almost linear with the problem size. But like I mentioned, the MISOCP introduces large error on the voltage profile as it ignores the phase coupling. So it is basically based on the phase decoupling approach. Then MILP seems promising and is more accurate than the MISOCP version and MILP based on the Lindy-3 flow. However, we further need to investigate the accuracy of the MILP and the large-scale feeder, and find out a way to improve the accuracy if possible. And of course, the last point here is we need advancement in the modeling, and not only in the modeling, also in the solution algorithms to solve the mixed integer type of problems that can be applied for solving the large-scale DoPF. That will ensure scalable and optimal voltbar control solution for the distribution feeder of the future. So these are the main takeaways from our work so far, and some of them are already published, and some of them we are going to submit for the publication. So if you have any questions on the models and methods, you can send me an email, and also have listed some of the references that could be useful. And then, like I mentioned, some of the work I presented are taken from these 3 papers of ours, 8, 9, and 10. The last part, MILP, is still not published. So if you need more information on that, you can reach out to me. With that, so I conclude my presentation, and I'm open for the questions.
Thank you. Thank you, Dr. Paudyal. Can you hear me?
Yeah.
Getting a strange echo. Okay, awesome. All right, so we have some questions from students. Let me actually first do the applause from online version. So there's one question from student. As relaxations cause error in the solutions, is there a method to quantify the uncertainty created by the relaxed solutions?
Yeah, well, I think so, it is rooted to the SOCP model. So since we use the SOCP model, you can quantify how far you are from the tightness, but you cannot guarantee where the solution will land before solving it. You don't have that a priori information, but once you solve it, you can at least find out how far you are from the tightness, because exactly the boundary of the SOCP, and then you can find that distance, which is basically the constraint in satisfaction, right? The equality constraints in satisfaction. So that gives a measure of the tightness of your solution.
Great. So the other question is on which form of the optimization model are currently being used at the utility industry? And if MILP, then how are they tackling the curse of dimensionality and convexification issues at their end?
Yes, this the DoPF with the mixed integer. There are not that many tools in the commercial domain, and even if they are using it, so they're kind of using some sort of the voltbar optimization by simplifying the grid model extensively. So that is, I think, the state of the art in the existing commercial tools. So they don't really have a comprehensive tool that can solve a large scale problem, and that's is accurate as the exact formulation. So yeah, I have looked at some of the tools that ETAP has, and also Power Factory, and in a couple of others. But yeah, it doesn't scale up for the large scale feeder.
Yeah, that's one of the challenges, right? To really make these algorithms work with the systems here. Okay, so the next question is again on compute. So it's what's the advantages, what advantage that does MISOCP gives with respect to MILP or MISDP in terms of compute time?
Yeah, so the MISOCP, so when we started solving it, we thought that MISOCP should perform as good as the MILP. Being the SOCP also a convex problem, and there are a lot of good solvers out there that can solve the SOCP. But then when we did that for the mixed integer SOCP, then we realized that the scalability and robustness of the solver in solving the MILP is far better than the solving MISOCP. So we could solve large scale MILP problem using off-the-shelf solver without any issue. But for solving the MISOCP problem, for large scale problem, we encountered some issue. We were able to solve conveniently for the small scale problem. Maybe it's a limitation on the solvers. The solvers out there are not robust yet to handle the large scale MISOCP problems. But maybe in the future, because it's the same methodology you can use, branch and bound and other techniques and other tricks in the mixed integer SOCP as well. So yeah, so these solvers are not robust to solve large scale MISOCP problem as compared to the MILP problem. That's the one thing, that's the one limitation that limits why we cannot use the MISOCP problem. Now the second is from the approximation error. So the SOCP does not include the mutual coupling, like I mentioned. I mean, the SOCP, at least the one that I adopted, does not include the mutual coupling. So that introduced large errors on the voltage profile. So you can comfortably use SOCP for the single phase circuit and also the decoupled three-phase circuit. But when it comes to the three-phase mutually coupled circuit, I think it will give you the more error. Then on the other hand, the MILP model, they can do the mutual coupling, but then there are the limitation on where you can use the MILP formulation because it does not include the losses. So if you cannot really use it for the loss minimization problem unless you find a way to approximate the linear model of the loss component on your model, then you can use it. So there is a trade-off, the application wise plus the accuracy wise, and also what solvers are available out there in a commercial domain.
So I was recently looking into it and I saw that Cplex is coming up with an MISOCP solver as well, right? So did you had a chance to test that? Because their MILP solver is kind of state of the art, right?
Yeah, that's right. Yeah, no, we have not tested it. I think we tested the Mosaic on this work, and it works fine. The MILP model, the Mosaic solver performs very well, even for the MISOCP large scale feeder. So we have seen it works, but few cases, and when we did some, a multi-period setup in MISOCP, it failed. I don't know if it is. The algorithms or solver is not robust yet to handle large scale problem. But no, I haven't tried the Cplex, but I love to try that Cplex person.
So I think there is one clarification question. So the question is that if you have integer variables in OPF and you get an MISOCP kind of model, that problem is the problem is still convex?
No, it's not. It's called the mixed integer convex because the way that they define this problem is if you relax the integer and if the problem is convex, it's called the mixed integer convex. And that class of problems are relatively easier to solve than the MINLP counterpart, right? Because when you do the branch and bond, for example, then the underlying model you have to solve is the SOCP, which is the convex problem. While in the MINLP problem, even if you do the branch and bound, you still solve the nonlinear model in each instance of branch and bound, which is still a NP-hard problem to solve. So that's why it's still non-convex, but there are robust solvers that can solve this class of problems, and particularly mixed integer linear type of problems, right? So without any issue.
So I don't see any other questions from students. Anyone else with a question? If you want to unmute and ask. Okay. So I'll go ahead. I have a question. So Sumit, can you comment on the optimization at distribution level, and running any optimal power flow requires us to have measurements, right, at a more frequent interval to be gathered from the network and work with them. So can you maybe talk about what do we have available right now and what kind of optimizations or optimal power flow we can realistically implement at the distribution level? Different time scale separation that you talked about, looking into the continuous variable or fast time scale. What are your thoughts on how we will get how and what we can work with OPF at the distribution level as of now?
Yeah, so I think there are models that look at the measurement based approach as well, like you mentioned. So I have seen that a couple of works coming out. They basically just look at the feedback measurement from those voltage, the nodes, and then drive the solution towards the OPF without really solving the OPF problems. That was really interesting. So so that is kind of like a approach where you don't really solve the large scale OPF problem, but you take the feedback from the the nodes, and then you drive your solution towards the OPF. And I think that is promising for the real-time applications, and that probably requires less communication need compared to the centralized approach that we are talking here. So that is definitely, I think, interesting to look at, in the OPF framework. And there are a bunch of a distributed approach coming. Again, they have the limitations, about the communication, the failure, and then also, sometimes the number of iteration it takes. But I mean, I've seen centralized and distributed approach, and then provide the benefit, right, in the convergence as well. So yeah, I think those are my viewpoints, that you probably need a method that scales without need for the much communication, and then also kind of provides the solution that is closer to the optimal solution.
Makes sense. So okay. Again, there is some echo, but I'll go ahead. So I think we have last 3 minutes. So I wanted to thank you for your time today, and for talking to us, and for giving the talk and speaking with our graduate students. So before we hang up, do you have any expert opinion or expert comment to share with the students who are working in the distribution level optimization or distribution systems automation and control? We have a lot of grad students working in this area, so they would like to hear from you what your thoughts are, and what do you see where this field is going, and some final comments from you.
Yeah, well, I think like one of the students pointed out, wanted to know actually what are the tools available there in the commercial domain that can solve this kind of problem. And I think there are very limited tools, that can help you basically from the commercial side, of the self tools that can be used for this purpose. So I think this is a very exciting domain, and it requires the knowledge from the control optimization, and has a very exciting career, I think, in the future. So I think don't stop the good work. So keep doing it. And I really like this area. Is from my PhD work, was focused on the three-phase DoPF, and then started looking into this convexification and other. It's really a very nice mathematical problem to solve, and that what should intrigue all the researchers, right? So I think it's a very good work the good domain to work on. So
Excellent. Thank you so much. So thanks for your time today, and I'll let you go. And again, thanks for the talk, and for talking to us. And probably students will reach out to you if they have any additional and follow-up questions.
Sure.
And I think we have your email. So and we did have your presentation recorded as well. So thanks so much for your time today. Have a great day, everyone. Bye.
Well, yeah, thanks. Bye.
Thank you.